We're going to look at heat of neutralization and the experiment. So we're going to define heat of neutralization, we're going to explore the heat of neutralization experiment, and we're going to complete calculations based on heat of neutralization. So to begin, we need to define heat of neutralization, and heat of neutralization is the heat change when 1 mole of H plus ions from an acid react with 1 mole of OH minus ions from a base. Heat of neutralization will always be an exothermic reaction, so again that means delta H is negative. That's a similarity with properties of heat of combustion. The essential reaction taking place in a neutralization reaction is actually the formation of water, where the hydrogen ion combines with the hydroxide ion to form water, and heat of neutralization is measured in kilojoules per mole. One of the most important parts of heat of neutralization on the Leaving Cert chemistry course is the experiment. So the experiment explores determining the heat of neutralization of the reaction between hydrochloric acid and sodium hydroxide. Now, there's certain steps to this experiment, which is the method. So in most cases, you would measure 50 centimeters cubed of hydrochloric acid and sodium hydroxide in separate polystyrene cups. You would record the temperature of each of the solutions, and before continuing any further, you need to ensure that the temperatures are the same. You quickly add the sodium hydroxide to the hydrochloric acid. You cover it immediately with a lid and you stir. Then what you do is you look at the thermometer that is in your solution that's now been mixed, and you record the maximum temperature. And then you calculate the heat of neutralization using the formula. And we'll be using the formula that we discussed in our previous video about the heat of reaction. But before we do a calculation, let's look at some common questions that come up on the exam related to this. So this came up in 2013 as question 3, and the next few questions are some sample questions that came up that year, and also other ones that could potentially come up if this was to come up as an exam question in the future. So the first question says, what is the purpose of placing a lid on the cup? So the reason the lid is placed on the cup after the addition of the sodium hydroxide to the hydrochloric acid is to prevent any loss of heat, as this would affect the temperature change. The next question is, why is polystyrene cups ideal for this experiment? And the reason they're ideal for this experiment is they are good insulators of heat, so they prevent loss of heat to the surroundings. The next question, would you expect similar answers if you completed this experiment with nitric acid? And the answer is yes, because hydrochloric acid and nitric acid are both strong acids. Another question you could be asked is, how could error be reduced in this experiment? And there's multiple ways error can be reduced. So error can be reduced by using a digital thermometer. You can use a pipette to measure the volumes of your solutions rather than a graduated cylinder. So you could pipette 25 centimeter cubed portions of each of your solutions until you reach the required volume. And then you could ensure that there's no splashing when you add your two reactants together, because you don't want any of them to get stuck to the side of your polystyrene cup. And also using the lid as we previously mentioned. The last question then is, why is the value of heat of neutralization for a strong acid and a strong base always the same? So when you react a strong acid and a strong base, why is heat of neutralization always the same? And that's based on what we said on the last slide. It's that the same reaction is happening all the time. The key reaction with neutralization is the hydrogen ion reacting with the hydroxide ion to produce water. And this will always have a heat value of minus 57 kilojoules per mole. All the other ions that are present are just something called spectator ions, and they're not involved in the main part of the reaction. So when calculating heat of neutralization, you can use the heat liberated formula that we discussed in our heat of reaction video. And this formula is M by C by T2 minus T1. Now, M is the mass of the solution in kilograms. C is your specific heat capacity, and your specific heat capacity will always be given to you in the question. And then T2 minus T1 is just your rise in temperature. So some questions will give you the temperature rise straight away, or some of them will give you the temperature that you have at the start, which is T1, and the temperature you have at the end, which is T2. The steps to calculating heat of neutralization is always write down your formula and then write down all of the above terms. But the key thing would be to check your units to make sure you have everything in the correct units for the formula. Find the heat liberated in the reaction using the formula. Then you need to calculate the number of moles of acid that you actually neutralized using the volume by molarity divided by 1000, and then find the heat that would be liberated by 1 mole, because this heat liberated formula will only be for the number of moles of acid you actually neutralized that you'll have gotten from step 3. So you'll need to find how much is liberated by 1 mole then in step 4 to find the heat of neutralization, because heat of neutralization is linked with 1 mole if you check your definition. So let's do an example. It says an experiment was carried out to measure the heat of neutralization of nitric acid and sodium hydroxide. The following is the equation for the reaction. Using a polystyrene cup, 200 centimeters cubed of the solution is 1 gram per centimeter cubed, and the specific heat capacity is 4.060 kilojoules per kilogram degrees Celsius. So we can see from the question that everything we need is given to us. So the first thing you're going to do is you're going to write down your heat liberated formula, which is M multiplied by C multiplied by T2 minus T1. So M is the mass in kilograms, but we can see that we're given 200 centimeters cubed. So, but we are given the density. So if we do volume by density, we can find the mass. So that gives us 200 grams, but we want that in kilograms, so we have to divide by 1000, so we get 0.2 kilograms. The next thing we want to do is C, which is our specific heat capacity, which is 4.060 kilojoules per kilogram degrees Celsius. And then we get our temperature change, so T2 minus T1, that is equal to 6.9 degrees Celsius. So step 2 is to fill in. So step 2, fill into the formula. So I'm going to have 0.2 by 4.060 by 6.9. And when I put that into the calculator, I get that my heat liberated will be 11.2056 kilojoules. So that is step 2 done. Now we need to go and do step 3, and step 3 is linked with the number of moles of HNO3 that are neutralized. So we know that our formula is volume by molarity, and that is divided by 1000. So the volume that we used is 200 centimeters cubed, that's from the question. The molarity is 1 mole. Then we divide that by 1000, and we get that the number of moles of HNO3 that were neutralized is 0.2 moles. So now I know that 0.2 moles represents 11.2056 kilojoules of heat. So if I divide both sides by 0.2, that will get me what 1 mole is, and we figure that 1 mole is minus 56 kilojoules per mole. At this point, we can check our answer, because we know that the HNO3 and the NaOH. The key reaction that we're looking for there is the H plus and the OH minus going to produce water. And I said in an earlier slide that the approximate value for that is minus 57 kilojoules per mole. So the fact that we've gotten minus 56 means that our answer is correct. So a key thing to note here will be if the neutralization reaction is 1 mole of acid giving 2 moles of H plus ions, you have to divide the heat by 2 at the end. So in a sample reaction here, we've got the sulfuric acid producing 2 moles of water. We can see that there's 2 H plus ions, so that must mean we have to divide our heat by 2 in that situation. So that's just important to be aware of. Now, sometimes heat of neutralization can also just come up as a separate calculation by itself without the experiment. And in those cases, often the specific heat capacity isn't given, but the overall heat capacity is. And if this is the case, you follow the following steps. First thing you do is you use the formula heat capacity by temperature change, so the mass does not appear now. So the steps would be to calculate the number of moles of the acid you're using, calculate the heat liberated using the formula, and this will be for the number of moles from step 1, and then you find the heat that will be liberated by 1 mole as per our last example. So this step here is like step 4 in our last example. So let's go through an example. It says an experiment was carried out to measure the heat of neutralization of hydrochloric acid and sodium hydroxide. The following equation is for the heat of reaction. Using a polystyrene cup, 50 centimeters cubed of each reactant 1 molar solutions were mixed and the rise in temperature was found to be 6.7. The density of the solution was 1.0 grams per centimeter cubed and the total heat capacity was 420 joules per Kelvin. Calculate the number of moles of acid neutralized in this experiment and consequently calculate the heat of neutralization. So they may leave out this part here to calculate the number if you're using heat capacity or specific heat capacity. So in this question, we see we're using heat capacity, so we know we're going to use our second formula. So, as we've said, step 1 is to calculate the number of moles of HCl that are used, and to do that we use the formula volume by molarity and we divide that by 1000. So the volume that we use is 50 centimeters cubed. The molarity is 1 mole and we divide that by 1000 and we get 0.05 moles. So step 2 now is to calculate the heat liberated, and that is done by doing C by the temperature change, T2 minus T1. So C here is our heat capacity, and our heat capacity is 420, and our temperature change is 6.7. So that gives it to us in joules, which is 2,814 joules. However, we usually want to get heat capacity in kilojoules because we want our heat of neutralization to be in kilojoules per mole. So to do that, you divide by 1000 and you get 2.814 kilojoules. Now, this kilojoules represents the number of kilojoules that are present in 0.05 moles of our acid. So 0.05 moles is equal to the 2.814 kilojoules. So to find what 1 mole is, you divide both sides by 0.05 and you get that 1 mole is equal to 56.28 kilojoules per mole. But we know that heat of neutralization is always negative, so that must mean that our heat is minus 56.28 kilojoules per mole, and the minus coming from us knowing that it is an exothermic reaction. So that's it for this video. Have a read over the learning intentions to make sure